Okay, so I'm trying to remember where we left off, and I didn't mark it. Did we do this slide? Talking about IDEs. Is this where we stopped?
We made it all the way through the MAT.
Oh, okay. To here? Okay, so again, these are all the same as far as the names go. Is that where we left off? Yeah. Okay, good. All right, a little further along than I thought. Hang on a second. All right. So the MHC molecules, you need to know what MHC stands for. Major histocompatibility complex, MHC. Did I talk about this at all?
Yeah.
Okay, so what's the deal with these MHC molecules? Alright, they're sort of the ID tag so that your immune system can key into those molecules and determine whether they're part of you or whether they're not part of you. And that's the non-self discrimination that's critical. If it's part of you, they need to know to ignore it. If it's not part of you, they need to know to go after it. And this is the basis of tissue compatibility. That's how I get the name. Tissue compatibility complex, the basis of tissue organ rejection. Alright. So, this idea of antigen presentation. So, we have several different types of cells. We've gone over B cells. And B cells have, these are circulating in the bloodstream, right? Type of leukocytes. And they hang out in the lymph tissue and wait for lymph-carrying pathogen to wash by. And B cells all have, their antigen receptor on them. But B cells can only bind sort of free-floating antigen. Okay? So free-floating. Either blood or lymph. And that antigen just wanders by, they interact, and if it binds to the B cell and the B cell gets stimulated, then it goes through this B cell activation. So B cells can only bind free-floating antigen. They can't bind anything hiding inside of cells. So if you have an infected body cell over here and it has a virus inside, the B cell can't do anything about it. Can't see it. It's got to be outside, free-floating. So the virus, if it's out here, the B cells and the antibodies can bind to it. All right. So this is the idea now of antigen present. Oh, wait, let's turn it off. Let me know if you like this lighting pattern or this lighting pattern. Yeah, me too. So two types of antigens. There are endogenous and exogenous. So the deal with these this idea of antigen presentation is, here's the cell. There are going to be two types of cells that we're going to be looking at, and they have an MHC molecule on them. So the MHC molecule itself is genetically determined. Has a particular shape, and T cells are able to recognize that shape. Now, the antigens, what's going to happen with this antigen presentation is that the cell, and we'll distinguish between the two types in a moment, but the same case in both, the cell will take some of that antigen that's inside, it gets partially digested and chopped up, so partial digestion, and then a fragment of this antigen gets folded in to the MHC. So this is the MHC, and this is the antigen fragment. So these MHC molecules are doing two things. They're acting as an ID tag, and they're holding a piece of an antigen on its surface. And this is the presentation. These are the cells. They come up with an antigen, gets inside, they partially digest it, and then they put it out on the membrane, on this MHC, and say, hey, check this out, look what I've got. And then the rest of the immune system has to come by and check it out. And if it's part of your normal cell, then they just ignore it. But if they're holding out something that looks dangerous that they don't recognize, then they get excited. Okay? So that's the idea of antigen presentation. So, endogenous antigens. These are antigens that come from inside the cell. They may be normal cell proteins. They may be bits of lysosomal membrane, or lots of pieces of maybe an actin filament that broke down. Or maybe it's a piece of a mitochondria that blew up, worn out, and got partially digested. And fragments of it then go out onto the surface. So these are endogenous antigens, antigens that were generated inside the cell. Okay? Now they could also be viral proteins. And remember how viruses, the virus life cycle. So the virus has to get into a host cell, which is one of your body cells, so host body cell. And viruses work by taking over that machinery inside the cell and take over the transcription and translation so that the cell now starts making more virus. Okay? Now, it could kill the cell, but the cell is gasping along at this point. So there are viral proteins in the cell that are from within inside, so these are generated by the virus. Some of those virus proteins also get built into this constant antigen presentation model. So here's the MHC molecule again. And in this case, some of that viral antigen gets presented out here on the surface. So in this case, it's a viral antigen, but it still came from within inside the cell. So it's endogenous. It's normal, well, the virus isn't normal, but that's where the antigens are being generated from, as opposed to exogenous, which we'll do in a minute. Okay? So this viral antigen is now presented on the body cell. Maybe this is a respiratory cell, and you have a respiratory viral infection, a cold. Well, those cells of the respiratory tract that have become infected with that virus, remember viruses are very specific for the cell type, and infected that cell type, the virus is living inside the cell, make more virus. The cell, before it dies, it sort of takes some of the proteins, puts them out on the MHC, and is hoping that, well, I don't know, I shouldn't talk anthropomorphically. It just presents the antigen on the cell surface. Now along comes a cytotoxic T cell, recognizes that antigen as not part of self, and pulls the trigger and kills the cell. That's where we're going. Okay? So it's really kind of amazing that these immune system cells, the T cells, I'm flashing laser light or something, that these immune system cells are able to recognize, you know, bits of an actin filament, bits of a mitochondria as normal stuff. They've learned to ignore it. It's supposed to be there, and they'll pass by that. But other proteins, fragments of stuff that are built into that they don't recognize they'll get excited and mount an immune response. So those are endogenous antigens. Same idea or similar idea for exogenous. Here is a cell. Now this is a wandering macrophage, or it could be a B cell. There are a couple of different types of cells. So we'll call this, let's go ahead and just call it an APC. And APC stands for antigen presenting cell. AG presenting cell. Now, the body cells are also presenting antigen, but these are special antigen presenting cells. And these are, for example, macrophages. I have a slide on this in just a second. Dendritic cells, which are off in the skin, they're like those Langerhans cells, and B cells can also do this. So this is what the APCs do. They process exogenous antigens. So imagine this is a macrophage. Well, it gobbles up a bacteria or some sort of antigen, goes inside the cell, it's endocytosed, right? So there's the antigen now inside the cell. There's a slide coming up. That antigen gets partially digested and then put out onto a MHC molecule, a little different one. And again, there's the antigen fragment. So the only thing I'm pointing out is endogenous antigens versus exogenous. This antigen came from outside the cell, brought in, chopped up, and then presented. The endogenous antigens are sort of generated inside the cell. No endocytosis going on over here. Okay.
Does that happen with anything other than viruses?
Well, some bacteria can get into cells. Cells can become cancerous or precancerous and start to present abnormal proteins due to their goofed up genetics inside. Okay, here we go. So here's what I was trying to draw. These are the antigen presenting cells. Okay? And they're exogenous antigens that are endocytosed, partially digested, and presented on the surface of an MHC2 molecule. So here you have to distinguish between MHC2 and MHC1. The antigen presenting cells, these guys, is an MHC2. Probably the second type that was discovered. And on the body cells, all of your host body cells are MHC1. So all of your nucleated body cells, so all you do basically is get rid of the red blood cells, all of your nucleated body cells have MHC1 on them. The antigen presenting cells, in addition, have MHC2. So there's the MHC2 protein, lysosome. This is just endocytosis. There's a fatty lysosome. So the little sharp, little pointy fragments, triangles, sheared off during partial digestion. Those little antigen fragments get built into these MHC2 molecules and presented on the surface. So this is an antigen presenting cell. For example, a macrophage, displaying antigen fragments. Or is this okay? Antigen presenting cells, exogenous antigens out on MHC2. Yeah.
So macrophages the only one that have the MHC2 protein?
No, the B cells and dendritic cells also can do MHC2 and act in the same way as this picture. Steve?
Is the MHC receptor complex type, are you only finding it on macrophages, dendritic cells, and B cells? It doesn't.
MHC2?
Yeah.
Yeah.
And do they does MHC1 not exist on those tests?
No, I think MHC1 is also on here as well. Yeah.
So what's the benefit of the MHC2? Why is it presenting just a fragment? They give the MHC1, it would, so that other red blood cells can attack and kill the cell. They're not doing that with this, are they?
Yeah, we don't want to kill the macrophage. All we want to do is alert the T helper cell to be on the lookout for this diamond-shaped triangle.
It's kind of just a way of being like, look what I found.
Pardon me?
It's kind of a body's way of being like, look what I found.
Yeah.
Go find it. Or
Uh-huh.
not.
Mm-hmm. There's stuff that it pulls in from outside. Check this out, it's in the neighborhood. You know, and then there's other stuff that it pulls out from internally. Whoa, look what's growing inside me. Is this okay? I don't know. Check it out. Alright. So here's a summary of the MHC1. So on all body cells, not red blood cells, they're all nucleated, essentially all nucleated cells. So MHC1 presents only endogenous antigen fragments. They're partially digested. These are normal self-antigens. Maybe. They could also be viruses, but they're presented inside. And so the MHC1 here interacts with the cytotoxic T cells, with these TA or CD8 cells. So, here's the body cell, and antigen presented on the surface of the MHC1, the body cell. Along comes a cytotoxic T cell. It has a specific receptor also, and if that specific receptor binds with this and it gets activated, this is a secret handshake sort of thing, then the cytotoxic T cell has to make a decision. Is that normal or abnormal? So, if it's normal on the screen, if self-antigen in MHC, if it is a self-antigen in the MHC, normal mitochondria fragment, more normal actin fragment, whatever, if it's normal, if it's supposed to be there, the cytotoxic T cell ignores it. No problem. Let it go, it's doing its business. However, if it's a non-self antigen in that spot from a virus, then the cytotoxic T cell kills the body cell. Kill the body cell, disrupt the viral life cycle, get rid of the virus. Okay? So that's MHC1 on body cells. If it's an exogenous abnormal, if it's an abnormal fragment, kill it. If it's an okay antigen fragment, leave it alone. And that's what the immune system has to do all the time. All of your cells constantly. Alright. MHC2 is on antigen presenting cells, and here's the list. Macrophages, dendritic cells, and B cells. These act as APCs, antigen presenting cells. And they present only exogenous antigen fragments in the MHC2. Okay? So if you endocytosis is presented on MHC2. And these antigen presenting cells interact with the T helper cells. So again, we don't necessarily want to kill the macrophage. It already digested up part of this virus. The virus is gone. So if it's a self-antigen in the MHC2, again, the helper T cell ignores it. Okay, everything's fine. It's a self-antigen. If it's non-self-antigen, the MHC2, then the T helper cell becomes activated. And T helper cell activation leads to mitosis, clones, and releases various signal molecules, cytokines, etc. to wake up the cytotoxic T cell and B cell. It gets kind of complicated, but they interact. So the helper T cells will help both the B cells and the CD8 cells to get active and mount a response. So this is antigen presentation. Antigen that can't be seen, that's not free floating anymore. Questions? MHC1 and MHC2. Endogenous versus exogenous. Alright, so here's summary maybe, or another summary. So, all body cells have MHC1. And they present endogenous antigens. That's what's on the MHC1 of all body cells. And they're monitored by the cytotoxic T cells. So if there's something abnormal inside the cell, the T cell kills it. If it's normal stuff inside the cell, presents it on the MHC1, T cell ignores it, but it's normal. The antigen presenting cells, they all have MHC2. And that's where they present fragments of exogenous antigens, things that they endocytose. Again, monitored by the helper T cells. If it's a normal protein, the helper cells just ignore it and go on their way. If it's an abnormal fragment in the MHC2, then the T helper cells wake up, sound the alarm, and get an immune response going. It's okay? So, new topic.
I have a question for you, Brenda.
Yeah.
So if the ABCs also have MHC1, if they're presenting something, what happens? Since you don't typically go and kill a macrophage.
I think the same thing goes on. If the macrophage has, where's my macrophage? Here's our antigen presenting cell. It would also have MHC1. I don't know, let's say it becomes infected with a virus or some other parasite, and it's presenting foreign antigens on its cell surface on its MHC1, this would get killed also,
Okay.
presumably.
So depending on that MHC complex and its presentation will be dependent on what section of the immune system responds to it.
Yeah, right. That's this idea.
Yeah.
Right. The cytotoxic T cells are monitoring the endogenous picture. And that's who's going to, pull the trigger and assassinate those cells.
Kind of a division of labor.
Yeah. Okay. Anything else? New topic, anaphylaxis. Alarm, fire codes. It's an acute allergic reaction or hypersensitivity, and they come in various different types, type 1, type 2, but they're hypersensitive allergic reactions. So same header up here for a number of these slides. Anaphylaxis is an allergic hypersensitive reaction. Anaphylactic shock can be life-threatening. People die from this. Here's the setup. Here's how it works. And again, this is what happens with things like severe peanut allergies, severe bee sting allergies, etc. Things that some people are dangerously sensitive and they can die from these if not treated. So here's the setup. This should look familiar. This is the first encounter with the antigen. This is when the body becomes sensitized to it. No symptoms. First bee sting, first encounter of peanuts, first encounter of poison ivy, no symptoms. But the B cells and the T cells have become activated to make clones of themselves. So, okay, we made that. And then remember the story about the antibodies, class IgE, right? Those are made and against that antigen, and they became attached to the surface of mast cells and basophil cells. Right? Remember that picture? We had the IgE antibodies stuck on the surface of the mast cell and the basophil acting as an antigen receptor. Everybody with me? All right. So remember, note, basophils are circulating, mast cells are not circulating; they're out in the tissue. Many of them are associated with epithelial membranes. So the intestinal mucosa, the respiratory mucosa, Some of the symptoms early symptoms of people having an anaphylactic reaction, diarrhea. Boom, it comes on right now. Swelling of the airway, the tongue can start to swell and close off the airway, which will do you in. And that's lethal. You can't close off the airway. They can happen very rapidly. And what happens is that the IgE antigen receptors on those mast cells and basophils, where am I? For the next encounter with steam engine. Sorry, I have to go to the next slide. So here's a subsequent exposure to the same antigen that we sensitized the cells to in the previous step. So the antigen now binds to those receptors on the basophils and mast cells, causing them to release large amounts of histamine. Okay? So if it's in the mouth and you sensitize cells on the tongue, the epithelium, and all of a sudden those start to release histamine and causes tissue swelling, the tongue swells, the tissue swells, we've got a mess on our hands. So you have this widespread or systemic histamine storm or histamine dump. It's released systemically, and you know what happens. The histamine causes systemic vasodilation and bronchoconstriction, and you get this double whammy. This is the life-threatening part. The blood pressure crashes. When it does, then you have anaphylactic shock. Shock caused from anaphylaxis. Okay? That's the blood pressure, and the airways constrict. So the bronchioles can constrict, swell up, close off. The upper respiratory tract can start to swell and close off. It's a mess. I think the next slides go for the treatment. But is this okay? Could you all write 3 or 4 sentences describing the anaphylactic sort of setup and how the shock develops? An anaphylactic reaction. Could you talk in terms of the sensitization period? No symptoms initially. And then on subsequent exposures, you have the symptoms. Now, some people become increasingly sensitized. So it doesn't necessarily go from no reaction to full-blown life-threatening reaction. It can. It's kind of rare, but it can happen. Another pattern is where every time you have peanuts or every time you get stung by a bee, the reaction is a little bit worse. And you have to be watching for those, because you don't know how bad it's going to get. There was a student here a couple of years ago. We had just gone through this or something. He was telling me that his wife was actually right now having an allergic reaction to, I think it may have been peanuts or something. And he started casually telling me about how her tongue is swelling. Oh my gosh. Call 911, get her out of here, what are you doing? I think he finally took her to the ER, but he should have been, calling 911 and getting them to take her to the ER. So if she crashes in the ambulance, not in the front seat of the car. What's he going to do then? Right? I don't know. Drive faster, I suppose. So, alright. So, what do you do with anaphylaxis? The treatment is epinephrine. So, this is the EpiPen. And somebody who has a anaphylactic reaction, a hypersensitivity to bee stings, peanuts, as an adult, they should know that. They should be carrying their EpiPen with them in their purse or their backpack or whatever. They should have that ready. Because you don't know how fast the reaction is going to occur. How fast and how severe the symptoms will present. So, one of the, did I already talk to you all about how epinephrine is also It's only called epinephrine in this country.
Yeah.
Every other country in the world calls it adrenaline. So with the EpiPen, it's good to practice that. And you have to take the EpiPen, take the cap off, prime it, usually a twist, you're pulling the cap off, and then you take, and it's intramuscular, so you go right through the jeans, right through the clothes, into the thigh, and you leave it there for 10 seconds. So that the epinephrine can get out of the pen, get into the muscle, and start to circulate. You have to hold it there for 10 seconds. And then you call 911. Anytime you use the EpiPen, it should be an automatic call for 911 in addition. So two things, the EpiPen and 911. Now, you should also be aware that I don't know why, we have this tremendous resistance to say something's wrong. We can deny life-threatening situations with ease. We tend not to do it. You know, the guy that chokes on a piece of food at the restaurant, this is what they train you to watch for, right? The guy gets up from the table, and he goes off to the restroom, to the men's room, and he dies. He passes out, he chokes there, he dies right there in the restroom floor. Rather than sitting out there at the table, you know, and making a big scene, we don't like to do that. We'll deny it. We'll go off and die quietly in the restroom. So, you know, see somebody doing this, and they're heading off to the restroom, you get up and you follow them. Right? Same thing with the EpiPen. People don't like to use these things. They cost about $80, something like that. It's prescription, so it's expensive. So, you know, my wife, being a school nurse, has lots of kids carrying EpiPens. They have known hypersensitivity reactions, bee stings, peanut allergies, etc. So a kid comes in to my wife, and they're starting to show some signs, you know, and so you have to watch them. You call the parents. That's what she has to do. First thing is get a hold of the parents or 911. And a lot of them are very resistant to use the EpiPen. Oh, you know, I'll take them into the ER or something. Well, what I'm getting at is that a lot of people will deny that they need to use the EpiPen. If you're having an anaphylactic reaction, you need to treat it early. So you take the EpiPen, you use it, you spend the $80 or whatever it was. What's the worst outcome? I mean, what are negative side effects of an extra dose of epinephrine? Not much. For most of us that are healthy, you know, the heart rate speeds a little bit, the airways open up, no big deal. You know, it's not like it has negative consequences for most people. So you need to use that thing, and you need to use it early. If you wait until the tongue is swollen off and closed off the airway, and then you give the EpiPen, sorry, it's too late. They're dying. So, you know, you have to be kind of thinking in terms of, well, what am I going to do if there's an emergency? You know, the guy who had the heart attack at his desk, he's sitting there in his office having a heart attack and denying that anything's going on. No, you don't need to call 911. They called 911 anyway, got into the hospital, yeah, he's having a full-blown MI. Right there in his desk, denying that anything was wrong. So, oh, I feel kind of bad, my chest hurts, you know, I'm sweating, I'm red, you know, I got all these signs, my, you know, shoulder hurts. But I'm fine. What are you going to do if you come across somebody like that? You know, something to think about. I'm off topic. Well, not off topic maybe, but off track. So, alright, let's move on. So, epinephrine, this should be familiar to you now. The emergency treatment. So, epinephrine causes systemic vasoconstriction. You know what that does? Systemically constrict all the blood vessels, up goes the blood pressure. And I hope that you all sort of remember the types of adrenergic receptors. Alpha receptors are on blood vessels. Do you remember that? Okay. And when you stimulate those, you get the vasoconstriction. So, You know, you got this sort of thing, here's the blood vessels, and you have all this smooth muscle, you have alpha receptors on them, and the alpha receptors will bind both norepinephrine and epinephrine. Both of those will stimulate it. The norepinephrine from the sympathetic neurons, epinephrine, both of these from the adrenal medulla, so vasoconstriction. We've got this picture in mind. Okay. Epinephrine also causes relaxation of the bronchiolar smooth muscle, so dilation there. So I hope that you've got this picture in mind also. Here are the bronchiolar airways. Here's the smooth muscle, and on those are the beta-2 receptors. And they will both be stimulated by norepinephrine and epinephrine. They're just not innervated. So both of these are coming from the adrenal medulla. And that causes the smooth muscle here to relax or contract? Relax. Good. And the airways dilate. Beta-2, you know. New topic. And let's hear, yeah.
How do you become allergic to something? Does your body have more sensitivity to it?
Yeah, you know, that's part of the immune system. Why do some people become allergic to these things and others don't? Not everybody's immune system is the same. Some mount this hyperactive response, other people sort of tamp it down. Say, okay, that was bad, but it wasn't all that bad. We're okay.
And then, cause for me, every time I get stung by a bee, it gets worse.
Yeah.
So it's kind of scary because you never know how bad the next time's gonna be.
Have you had any airway tightening?
Yes.
Then you should be getting an EpiPen, my thought.
So, but.
Because you don't know next time if it's going to be even more severe.
Mhm.
Yeah, definitely. Get an EpiPen. Talk to your doctor. They'll prescribe one.
And then I have a cousin who's like so allergic to peanuts that he couldn't even be around peanut butter. But he couldn't even smell it. But now he can be next to someone eating peanuts. Like it doesn't affect him anymore. Why does?
Can he eat it or touch it?
I don't know.
Yeah, they probably haven't done that experiment.
They're probably not.
No, I think I'd hold off too.
But
Right.
just that he can be around it, do we kind of reverse as adults?
Well,
maybe?
yeah, that we can. It's variable. And the whole idea of allergy shots, if some people get allergy shots, they're allergic to milk, allergic to grass, allergic to cat dander, you got a long list. Well, you can go through this series of allergy shots, and what I believe the strategy is they're giving you minute quantities of the antigen, trying to get the immune system to recognize it, to make antibodies to that antigen slowly, so that as you encounter that antigen, then the antibodies bind it up and inactivate it. I believe that's sort of the strategy of those.
That makes sense.
But it's highly variable. I mean, you've been stung by lots of bees. They swell up, but that's about it. They make, a little walnut or lemon-sized bump on, swelled up. But it doesn't go any farther. My hands don't swell. My arm doesn't swell. But yeah, if it's getting worse, if you got airway tightening, I would talk to your doctor. Anything else? Yeah.
They also say that as far as babies, not to feed them food too early on, because that causes more allergy reactions later on.
Yeah, I don't know what the latest is on baby nutrition. Breastfeeding for the first year. I know that's not solely breastfeeding, but breastfeed for the whole first year is the standard, I think, best practice recommendation. And then I don't know where it is for slowly introducing food. I think you're supposed to start out real benign stuff. I don't know what that is anymore. Oat mush or something. Yeah, Steve?
The EpiPens, when you get them, you get 2 of them, and you also get a practice,
Oh, okay.
like fake one in the box with them.
Good.
So you can actually practice without having to worry about, injecting yourself with.
Right. And you should practice with it,
Yeah.
because there are a couple of steps you have to do
Yes.
to activate that thing, and you don't want to have you figuring it out, reading the instructions during the middle of the crisis.
I've noticed that going into puberty will change your antigen receptivity rate.
It doesn't surprise me.
It either makes you more sensitive or less sensitive. You know, example, when I was a child, I got stung by a bunch of bees. Didn't matter. But, 18, 19 years old, I get stung by a bee, and my tongue got fluid big.
Yeah.
One of those bands.
Yeah. So you carry an EpiPen?
Yeah.
Yeah, good. Right. Yeah, things change throughout different periods of life. Everything changes at puberty, though. Hang on. Okay. Vaccination. New topic. And what I would like you to do, leaving a college sequence of biology and science, is to understand those a little bit more. There's a lot of emotion and misinformation wrapped up around the whole topic of vaccination. I'd really like you to sort it out and think in terms of what's the evidence. Okay? So, here is some data. This was data that was presented in a JAMA article. JAMA is for the Journal of the American Medical Association. That and the New England Journal of Medicine are probably the two premier medical journals in this country. New England Journal of Medicine and JAMA. And the British, it's the Lancet. So here's some data that was pulled together and published in this article. I just stole the graphic here. This is pre-vaccine era morbidity in the U.S. Estimated annual morbidity. Now, morbidity is just getting sick. It's not mortality where you die. Morbidity is just coming down with it and becoming infected. So this is pre-vaccine era, and I don't remember. They define it in the article somewhere. Maybe mid-1800s or something like that. Okay. So you can see that. What is it? Diphtheria. What is that? 21,000 something or other. 21,000 cases. You come out with a vaccine, it's down to about 0. Okay? So most recent, I don't remember what the most recent data year was in this, but it's in the article if you want to read it. So you just go down to the list. I don't know what's that next one. Oh, H. influenza. Now, is this the seasonal flu? No, because that's Haemophilus influenza, that's the bacterium. Right? So, lots of cases, vaccine, few cases. So it just goes down to the list. Hepatitis A, hepatitis B, measles, mumps, pertussis. This is whooping cough, right? What is that? What did that used to be? Pertussis. Yeah, 200,000. 500,000 people used to get sick with that. And pertussis, whooping cough, we're having a resurgence of that?
And my son got it even after he had the vaccine.
Yep, so did my wife. She got it from some middle school kid.
He was in preschool.
Yep. They know that the vaccine isn't 100% effective. They used to think that it would be good for 10 years, I think. Well, my wife was vaccinated, but it wasn't getting, so the vaccine is wearing off. Or it's not that effective. It's not going to get 100% of the kids. So your child was one of those that, was unfortunate to get the vaccine and still get it. Now that happens. Lots of people get the flu shot every year and they still come down with the flu. That's going to happen. It's a numbers game you have to play. There's all kinds of, there's polio, rubella, congenital rubella, smallpox. So the point is that vaccines have drastically reduced the incidence of these diseases in the U.S. population. Okay? That's sort of the infographic message of that slide. For mumps, there's only, one cure, 99% of the cases of mumps. And, a lot of doctors these days have never seen these diseases, these childhood diseases. Used to be a doctor was trained in these. They'd recognize pertussis, mumps, measles right away. A lot of doctors right now have never seen these diseases in their training, in their whole career. They're just not out there. So the docs, nothing against them, but they're real slow to recognize pertussis. They haven't seen it. They don't get it. They don't, it's something new for them. So, all right, moving on. Here's another little data slide. This is number of diarrhea-related deaths per month among 11-month-old children in Mexico. This was published in the New England Journal of Medicine. It looks like about 2007 or 8, somewhere after that. So it must have been a couple years after that, I guess. So fairly recent, but that's where it's a good journal. So what does it show? These are deaths of 11 months old, and there's a little seasonal fluctuation every year, right? 2003, I don't know, there must be a spike. Maybe it's during summer, I don't know, and it drops off. And then it spikes again. Every year has the same basic pattern, right? Goes up again, and now they introduce the vaccine for some of this bacteria or viral diarrhea. And following year and subsequent years it goes down. It's pretty dramatic, graphic, for the effectiveness, the efficacy of vaccines against that disease in that population. All right. Here's an idea that I want you to think about and be familiar with. This idea of herd immunity. It's an important concept you should know when confronted by people who say, I don't believe in vaccines, I'm not going to get my child vaccinated. The reason they can do that is because that most of the children have been vaccinated. So there's this idea of this herd immunity. This comes out of animal science. You vaccinate 80 or 90% of your cattle. Well, you don't have to get every single cow. If you've got 80 or 90% of it, that's enough to prevent this disease from getting established in your herd. That's the herd immunity. And this is a good article. It's out of Wikipedia. You ought to go look at and read. It's short. Herd immunity, I'll just read the first little bit. Or community immunity describes a form of immunity that occurs when the vaccination of a significant portion of the population or herd provides a measure of protection for individuals who have not developed immunity or have not been vaccinated. Herd immunity theory proposes that in contagious diseases that are transmitted from individual to individual, chains of infection are likely to be disrupted when enough people are vaccinated and immune to it. So those parents that don't want to get their kids vaccinated are the only reason they're able to do that because most of the other kids have been vaccinated. Vaccination rates fall, pertussis went up. It was shown to be related to the pertussis vaccination declining. Rates go up. It's not a surprise. You stop immunizing people against polio, you can expect polio to start increasing again. It'll get a toehold and get going. Okay? So that I'd like you to read that. It's a relatively short article. So it's another, and then there's references. So it's just about 2 paragraphs long. I would like you to read that. You can just follow the link to it. Alright, so what about the autism? This is one of those that just amazes me that people still talk about autism and vaccination. It's an urban legend, it's an urban myth, and those things die hard. They're like conspiracy theories. It's very difficult to disprove a conspiracy theory, right? You say, where's the evidence for this theory? Well, there isn't any. The government's hiding it all. Right? That's why you don't see it. How can you disprove that? You can't. So you need to be thinking, well, where's the evidence for this? So I'd like you to read this article also. This one was published by CNN. It's not that long. Is that, the end of the autism vaccine debate question? Well, some people just die hard, and some ideas die hard. I'd like you to read this story, okay? Because I want you to leave this class, a little more educated, perhaps, on vaccines and what some of the attitudes out there are. When you make a decision, particularly a medically related decision, I would like you to base your decisions on the evidence. Is it evidence-based decision-making? Or is it just opinion and, fear? When you go to the clinic and you get medical care, what do you want? Do you want evidence-based care? I do. I don't want somebody saying, oh, well, I think I just need to go home and gargle with honey and sugar water. No, I don't know what it is. I want something that's got evidence behind it. So this idea of evidence-based decision-making. So read this, and here's the backstory. This is where it all got started. Back in '98, some British gastroenterologist produced a study, published it in Lancet. That's the premier British medical journal. It has a lot of prestige, a lot of people read it. And it carried a lot of weight, got a lot of people alarmed. They were talking about the MMR vaccine, which is the measles, mumps, rubella. And then, there's the story of thimerosal in here somewhere, which is the mercury. Trace amounts of mercury in the vaccine to keep from growing things. They subsequently got rid of the mercury. There's no more thimerosal in vaccines, but that was another idea that is causing autism. Now, the incidence of autism is increasing. It's rather alarming, the rate of newly diagnosed autism, and it's not just a better reporting phenomenon. There are, for some reason, the incidence of autism is going up. Okay, but there is no evidence that it's related to vaccination. Okay, so read this. All 11 authors of this original study, or I think most all of them, 9 of the 11 or something, in that Wakefield study have recounted and said, okay, it really wasn't the way that we presented it. The journal, Lancet, pulled the publication, and that is rare for a scientific journal to go back and pull an article that is already published. It said this was flawed research, it should never have been published in the first place. Lancet did that. They retracted it. That happens very, very rarely. So, go read that article too. It's not long. I say read easy. It's CNN. You shouldn't have any trouble with it. And here are some more websites for general vaccine info. If you are not familiar with the CDC site, go to these websites. Click on these links. CDC, you should know, is the Centers for Disease Control and Prevention. This is the U.S. U.S. Health Monitoring Network by the government. You ought to look at it, see what's there. It's a great resource if you're after evidence-based science. Voila. Any questions? All right. If there's anything, look over these notes and see if there's something that you want to review tomorrow. The other class, I had a little bit of time, so we went back and just, touched upon a number of different slides. If you all have anything that you want to go